Hello, everyone, and welcome to 3.5. This should be a pretty good section. I'm excited for it. So get ready to relax and enjoy as we talk about the derivative of trig functions. Now, really, there's almost nothing new in this section. Okay, there's some new formulas. Use the formulas. The harder part of this section is going to be remembering trig, maybe. So we'll see how that goes. We'll review it when we can. And this first video is really just gonna be like a motivational and theoretical inspiration of what's happening, okay? We're not actually solving any problems in this video, just giving context and showing where some things come from. So let's start by exploring, all right? And let me look at and talk about what you've got in front of you. So the blue graph, this blue graph, right? This is the graph of sine. So sine is 2 pi periodic. It repeats every 2 pi units and it oscillates between +1 and -1. All right. Now, what do I have over here? What is this orange graph? This orange graph, look on the left. This is an approximation of the derivative, right? If we take the limit of this orange function as h goes to 0, then this orange function approaches the derivative. So for small enough h's, the orange thing should be the graph. So let's look at what happens as we make h smaller and smaller. It's at 1 right now. So right off the bat. No, let's not go into that. Let's make h a little smaller, 0.5. A little smaller, 0.3, 0.2, 0.1, 0.01. 0.001, 0.0001. As h gets really small, what does this orange graph look like? You might notice that the orange graph is basically the same as the blue graph, just shifted over a little bit. Or if you're really good, you might say, Jason, that's cosine. And if you said that, you'd be correct. So the derivative of sine is just cosine. And this is kind of one of the ways to see where it comes from. And that's how we're going to start. Okay, so we got theorem, we'll give it a name, theorem 3.8 and 3.9, because 3.9 is going to be in a different video, but I want all of your derivatives in the same area. Okay, and that says that the derivative, and leave space for 6 things. The derivative of the sine of x is equal to the cosine of x. And likewise, the derivative of cosine of x is not equal to sine of x. It's equal to negative sine of x. And you could see that in the same way. So leave space for 6 more things. Sorry, 4 more things right here. Leave space for 4 things. We'll be filling those in a future video. Or you know what? Let's even tease it. We're going to talk about what the derivative of tangent is in a later video. And we're going to talk about the derivative of cosecant. Whoa. The derivative of cosecant, the derivative of secant, and the derivative of cotangent. Also, by the way, this is a new place since the last video you've probably have seen. Hope you like my new place. It looks a lot better than my last one, right? I also shaved. All right, let's move on to the next video. No, not the next video. The next part of the video, we're gonna show you where this comes from. We're gonna do a little proof. I shouldn't have said the P word. People don't like that. So to prove that the derivative of sine of x is equal to cosine of x, we're going to use 3 things. All right. First thing that we're going to use is that, oops. The first thing that we're going to use is 2 limit results that we talked about earlier. Remember this, the sine of h over h, this was one of our limit results in chapter 2 that we talked about. This limit equals 1. We're going to use another limit result from that chapter. You don't have to necessarily write these down if you want, but they can be helpful for context. This limit is 0. We're going to use this limit as well. We prove both of these limits at the end of the quarter, all right, using something called L'Hopital's rule. And then the third thing we're going to use is an angle sum formula, I believe. Yes, the sine of x plus h is equal to the sine of x cosine of h plus the cosine of x times the sine of h. If you're wondering why I'm only putting the h's in parentheses and not the x's in parentheses, it's because x's don't usually go in parentheses. And h's, I'm putting the parentheses to separate it from this function. Sinh, hyperbolic sine. You may or may not have seen that, but we're not dealing with hyperbolic sine. It's actually not as bad as it sounds. There's some cool things about that function, but we're not doing that here. Okay, so these are what we're going to use to prove it. So how do we prove anything? How do we prove any equation? Well, we prove some equation by looking at one side and then trying to show that it equals the other side. So if we want to start with one side, let's start with the left-hand side. Let's always usually start with the more complicated side, if anyone remembers that from proving things in like a trig or a pre-calc class. So the derivative of that left-hand side is literally the limit as h goes to 0 of f of x plus h minus f of x all over h. In this case, our f is the sine. All right, so you know where to go. You know where to go from here. You know how to start. Because I told you, we're going to use these three things. Which thing do you think we should use to start? Well, the one that we have, right? We're going to use this little guy. That little angle sum identity on that top. Oops, I erased my h. This is going to be the limit as h goes to 0. I haven't done this proof in a while, so I hope I remember all the steps. I didn't write that down in my notes. So it's going to be the sine of x cosine of h plus the cosine of x times the sine of h. And then remember, we still have the sine of x from before. Now we're going to rearrange things. So we want the sine of x's together. So we're going to put this guy with this guy and then leave the other part by itself. So let's look at the two red things and do a little factoring. We can take the greatest common factor of the red things, and again, the other thing is just going to be chilling at the end. So we're going to factor out a sine of x, and what we're left with is a cosine of h minus 1. And actually, believe it or not, we are almost done with this proof. We're almost there. Only a little bit is left. All right, don't mind this. It doesn't let you erase it when you copy it over, which is kind of weird. So now let's just split this into two fractions and two limits. We can do both of those as long as the limit exists. Remember, as long as the limit exists, we can split things up. And let me rewrite that first fraction a little bit. Write it as a sine of x times cosine of h minus 1 over h plus the limit as h goes to 0 of the second thing, which is cosine of x times sine of h over h. So again, I'm not doing anything super fancy, just splitting up this fraction into two fractions and splitting up the limit into two limits. And this works again. It works if both limits exist, which we don't know that yet, but we're gonna show it. And now look at what we have. The limit as h goes to 0 of sine of x, this has no h's in it, right? That sine of x can come out in front of the limit. Cosine of x, that has no h's in it. That's going to come out in front as well. So then we're really left with something really nice. It's sine times this limit. And this limit is one of the things that we know. plus cosine of x times this limit, which, surprise, surprise, is another thing that I said we were going to use. So this first limit we said was 0. The second limit we said was 1. We get sine of x times 0. Oh, that's easy. Plus cosine of x times 1. That is indeed just a cosine of x. We started with the derivative of sine x. We used the definition. We used an angle sum formula. We split things up. And indeed, both limits did exist. They were very nice limits. And we showed that the derivative of sine of x is cosine of x. You can do it exactly the same way for cosine of x. All right. For the derivative of cosine of x, use the angle sum formula, use the same limit formulas. And you could do this on your own, easy peasy, I believe. Might be good practice. Just use this proof as a mimic and then show it for cosine. That would be a good thing to do. And you can always let me know if you have questions. That's pretty much all I wanted to talk about in this video. In the next video, we'll do some practice utilizing the derivative and combining it with some differentiation rules from 3.3. Okay. Have a good day, and let me know if you have questions.